afternoon, everyone. My name is Osama Layadi, and I am a researcher in the field of smart energy management systems for microgrids. My current focus is on using multi-agent reinforcement learning for diagnostics in power transformers to improve overall efficiency and reliability in microgrids. Thank you for having me here today, and I look forward for sharing my research with you. Presentation today, I will be providing an overview of the current state of art in the field of smart energy management systems for microgrids. I will then proceed to elaborate on the utilization of multi-agent system deep reinforcement learning for diagnostics in power transformers. Additionally, I will present the architecture of the proposed multi-agent reinforcement learning system for SEMS. Finally, I will conclude by summarizing my findings and discussing their implications in the academic context. The ongoing energy transition to a smart grid is increasing the integration for renewable energy sources and new energy storage systems, which is having an impact on energy demand response. The power system is becoming unstable due to the variation in the power flows maintained by the power transformer, which are the most critical components in the system. These power transformers failures have a direct impact on the system and cause instability, outages, and fatal incidents at the highest cost. To protect these power transformers and maximize their availability, innovative approaches are needed. One proposed approach is to design a fully autonomous microgrid in multi-level from monitoring, auto-diagnostic to self-assessment and reliability by introducing smart sensors into power transformers, relying on power transformer maintenance experts to assess the overall health index of the equipment and inspect and label all necessary data using AHP or multi-criteria approach. The proposed diagnostic approach is based on smart energy meters, which are decentralized and blockchain based. In some cases, the data can be used to forecast energy needs in the grid and the energy demand to better calculate the heat index of the microgrid. The approach follows the model-based system engineering methodology. So, diagnosing power transformers using machine learning algorithms involves several key steps. The first step is power transformer online monitoring, which is monitoring the key performance indicators to identify any potential issues with the power transformer. These KPIs may include temperature data in different parts of the power transformer, such as the winding, the core, and the oil tank, as well as the levels of different gases resulting from arcing in the oil, water content, and electrical data such as the root mean square of current, voltage, interfacial voltage, power factor, and all necessary data. The second step is oil sampling for dissolved gas analysis, which is an offline operation that helps to identify any issues within the power transformer. The third step is inspection and labeling by experts who use their knowledge and experience to identify any potential problems with the power transformer and label also the data accordingly. The fourth step is prediction and classification, in which machine learning algorithms are used to analyze the data and make prediction about the heat index of the power transformer. These algorithms can be used to predict the likelihood of failure, estimate the remaining life of the power transformer, and identify any potential issues. The final step is visualizing the results in an open platform which is connected to a smart energy management system in the microgrid This platform allows the results of the diagnostic analysis to be easily viewed and understood by those responsible for the current state of the grid. The data is communicated to a smart energy management system that is controlling the grid component, scheduling the loads, adjusting power factor for an optimal state of the power transformer. As we said, power transformers are critical components in the microgrid, and their failure can have significant consequences. Some common failures in oil-immersed power transformer include insulation failure, winding failure, and oil leaks. Insulation failure can occur due to aging, overheating, or exposure to moisture, leading to a breakdown of the electrical insulation and increased risk of electrical arcing. Winding failure can occur due to overloading, mechanical damage, or exposure to high temperatures, leading to damage or failure of transformer winding. Also, we have oil leaks that can occur due to the damage to power transformer tank or oil seals. Also, it leads to the loss of insulation, oil, and potential damage to other components. To prevent or to minimize the impacts of these failures, power transformers are typically monitored using a variety of techniques. These techniques include online monitoring, dissolved gas analysis, infrared thermography, and regular visual inspection. Online monitoring involves the use of sensors to continuously monitor the key performance indicators such as temperature, current, voltage, power factor, etc., and also the levels of the existence of gases such as hydrogen, carbon monoxide, etc. So these two figures are summarizing the different type of failures and also describing the monitoring techniques, which is internal techniques such as thermal analysis, vibration, etc., and also external one such as monitoring the vibration through wavelet transform, also the OLTC and other computing techniques. Presents a summary of various studies that have been concluded on diagnosing power transformers using machine learning algorithms. The table lists the teams who conducted the study, the data the study was published, and the date the study was published, also the goal of the study and the methodology used, the algorithm employed, and accuracy. These studies listed in the table cover a wide range of goals, including general health assessments, internal fault detection, insulation condition assessment, incipient fault detection, oil quality, and the methodology used are basically dissolved gas analysis, discrete wavelet transform, improved Firefly algorithm, linear programming boosting, and other techniques. The algorithm used in these studies are time series, hierarchical ensemble extreme learning, machine, linear programming boosting, and SVM, sport vector machine, etc. So the accuracy of the results varies between the studies, with some achieving high accuracy levels of 98% or higher, while others achieve lower accuracy levels in the range of 60 to 80%. Overall, the table shows that machine learning algorithms can be effective in diagnosing power transformers, but the accuracy of the results can depend on the specific goal of the study and the methodology used and also the algorithm employed. Based on the table previously discussed, we have proposed a new architecture of power transformer health management or prognostic and health management, integrates both online and offline monitoring techniques, and is based on a layered approach where each layer communicates with the higher layer through human, hardware, or software agents. The agents are responsible for recording, analyzing, pre-processing, and labeling data, and then classifying the failures, providing prognostics and alarms that are displayed on a monitoring dashboard. This architecture communicates directly with a smart energy management system that is distributed throughout the grid, which is responsible for load scheduling, power factor adjusting, and maintenance planning with the help also of your human agent. To validate this architecture, an exhaustive list of algorithms were tested and classified to classify general failures such as thermal faults and discharges. The results showed that the use of the solid gas analysis can classify 4 levels of temperature overheating and 3 levels of discharges with an accuracy of 85.95% using support vector machine optimized using evolutionary algorithm with the radial kernel. The the solid gas analysis can classify only 2 levels of discharge and detect thermal faults by using random forest with an accuracy of 100%. However, these algorithms are highly dependable on the dataset. That's why the tested or the algorithms tested will be retested using deep reinforcement learning depending on the data. That's why we are including here the reinforcement learning method to increase the efficiency of the intelligent system. The discussed architecture is using or is describing the use of a multi-agent system for diagnosis and management of power transformer failures in the microgrid. The system is composed of different agents that are responsible for various features of the autonomous system, including monitoring, diagnosis, and load management. The environment is made up of the power transformer, the maintenance team, and the energy management system of the microgrid. The raw data from sensors, inspections, and energy demand forecasts are used as an input for different policies, which are modeled using machine learning algorithms such as random forest and support vector machine evolutionary radial kernel. These models have been found to have an accuracy of between 86 to 99% in diagnosing different defects. The agents are updated and trained using the max-min actor critic learning automation algorithm with rewards coming from the maintenance team and the energy management system. So, the figure represents the global architecture of the types of the agents in this approach, which are the human agents who are pushing inspections, assessments, oil sampling, and comments directly to the monitoring stage of the environment and enhancing the other agent through the reinforcement learning algorithm, which are currently under development. The hardware agents are representing the smart meters, smart sensors installed in the power transformer, the thermal camera, which is used typically for dry power transformers, These two types of agents can't be reinforced using algorithms, but using return on experience. However, the third type of agent, which is the software based on machine learning algorithms, as a policy and getting raw data from all states and communicating the results through the monitoring systems. All agents are connected to the smart energy management system agents, which is more complicated because it integrates different grid constraints and control the grid in different levels, from loads to distributed energy resources, using robust control and linear quadratic controls in order to optimize the energy consumptions and well manage the load to keep the grid and the power transformer in a more stable state. As we have seen, this paper presents an approach for connecting power transformers to a larger intelligent energy management systems in microgrids through monitoring using multiple software, hardware, and human agents, incorporating machine learning algorithms for the health index of the power transformer. The technique is based on multi-agent theory, machine learning, and automation, with the goal of creating a smarter and more digitized and autonomous microgrid through the multi-agent reinforcement learning algorithm for smarter power transformer diagnostics. The paper discusses also integrating this approach into a smart energy transformer with the goal of achieving a fully autonomous and reliable power transformer in the future. So in order to implement this type of system, we have now installed the different sensors in a real case study, and now we are having and acquiring enormous data which are monitored. And now we are classifying this data in order to get failures and pronostics for the power transformer. Thank you for your attention and consideration. We hope you found the information presented in this paper and presentation to be insightful and informative. If you have any comments or questions, please do not hesitate to reach out to us. Thank you.